Everyone, welcome to Circuit's Physics video tutorial. In today's episode, we look at one example of Compton scattering, known as pair annihilation. What happens when a proton and an antiproton particles collide elastically? Find out, stick around, watch and learn. The question is, an antiproton has the same mass and rest energy equal to 938.3 million electron volts as a proton, but has a negative charge instead of the positive charge of the proton. A proton and an antiproton, initially far apart, move toward each other with the same speed and collide head-on, annihilating each other and producing two photons. Question is, find the energies and the wavelengths of the photons if the initial kinetic energies of the proton and antiproton are, letter A, both negligible, and letter B, both equal to 545 million electron volts. Before the collision, both momentum and energy are conserved in a pair annihilation. So the proton and antiproton are initially far apart. So the initial electric potential energy, denoted by capital U naught, is zero, and the initial energy, denoted by capital E, is just the sum of the particles' kinetic energy Ke and the rest energy expressed as mc squared. The rest energy mc squared is given in the problem equal to 938.3 million electron volts. And after the collision, um, the final energy, all right, is the sum of the two proton energies. Okay, that is Ke plus mc squared. That's for one photon. And since there are two photons, so we have another Ke plus mc squared. All right. So this is because the total initial momentum is zero, hence the total momentum of the two photons must likewise be equal to zero. We find the photon energy E prime by using conservation of energy and the conservation of momentum. Therefore, we say that the final energy of each photon, okay, denoted by E prime, is the sum of its kinetic energy and the rest energy mc squared. And our target variables for letter A, we have the final energy E prime and its corresponding wavelength lambda. Okay, if the kinetic energy of the photon is considered negligible, and for situation letter B, okay, we also find the final energy of each photon as well as the corresponding wavelength lambda if the kinetic energy of each photon is given uh, equal to 545 million electron volts. Moving on to our calculations, the energy E prime, if the kinetic energy is negligible, right, is simply equal to the rest energy mc squared all right. So that means the final energy of each photon or capital E prime is just equal to 938.3 million electron volts. Its corresponding wavelength lambda can be determined using the formula lambda equals the product of Planck's constant small letter h and the speed of light small letter c divided by uh, the final energy E prime, right? So we first find the product of Planck's constant and the speed of light, that is 4.136 times 10 to the negative 15 electron volts second multiplied by speed of light 3.00 times 10 to the 8 meters per second, and the product is substituted here, okay, in the equation lambda equals hc over E prime. So 1.24 times 10 to the negative 6 electron volt meter, all right, divided by the computed total energy E prime, 938.3 times 10 to the 6 electron volts, all right, from 938.3 million electron volts, we converted it to electron volts, all right. So doing our math, we will get the value of the wavelength lambda, which is equal to 1.32 times 10 to the negative 15 meters. For case letter B, if the kinetic energy of the photon is not negligible, but is instead equal to 545 million electron volts, then the total final energy capital E prime of each photon after the collision is the sum of 545 million electron volts plus 938.3 million electron volts. All right? So that is equal to E prime of 1,483 million electron volts. Its corresponding wavelength, all right, again using the formula, lambda is equal to hc divided by E prime. Where earlier, we already determined the product of Planck's constant and the speed of light, that is 1.24 times 10 to the negative 6 electron volt meter, and divide that by this computed final energy A prime already expressed in electron volts, or 1,483 times 10 to the 6 electron volts. So doing our math, we get the wavelength lambda equal to 8.36 times 10 to the negative 16 meters. This is the wavelength that corresponds to the photon energy E prime of 1,483 million electron volts. A 650 nanometer visible light photon has energy equal to 1.91 electron volts. The photon energy we obtain in part A, which is equal to 938.3 times 10 to the 6 electron volts, is about 5.00 times 10 to the 8 times greater. So, as expected, the wavelength 1.32 times 10 to the negative 6 nanometer is indeed shorter than those for a visible light photon. And finally, to emphasize the key concept that we applied in this problem, in pair annihilation, a proton and an antiproton collide and disappear, and they are replaced by two or more photons. Energy and momentum are conserved in pair annihilation. So that's about all. Till the next episode, inshallah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.